This video discusses remainder theorem and factor theorem. Remainder theorem states if a polynomial p of x is divided by x minus a, then the remainder is p of a. So basically it's saying if your divisor is linear, if you find the zero of that divisor and plug it into the polynomial, it will give you the remainder if you were dividing by that divisor. Let's use remainder theorem to find the remainder of p of x equals negative x to the third plus 2x squared minus 5x plus 2 when divided by x minus 2. Remainder theorem says all we need to do is plug the zero of that divisor x minus 2 into the polynomial and we'll get our remainder. So let's start by finding the zero of x minus 2. That's going to be x equals 2. So we're plugging 2 into our polynomial. That's negative 2 to the third plus 2 times 2 squared minus 5 times 2 plus 2. It's going to be negative 8 plus 2 times 4, which is also 8, minus 10 plus 2. Adding all those together, we get negative 8. So the remainder, when dividing p of x by x minus 2, is negative 8. I want to do the synthetic division just to show you that if we actually did the division, we would get the same remainder. Oh, I put my 0 on the outside, my coefficients underneath. And then we perform our synthetic division, dropping down our first number, multiplying by the 2, add down, multiply by 2, add down, multiply by the 2, add down. We know the last number is always the remainder with our synthetic division, and note these two numbers match. Honestly, I don't use remainder theorem that often. I use it to check like 1 or negative 1, but I don't use this too often because I can do the synthetic division just as fast. And typically, after you find the remainder, there's something to do after that, which involves division. You may be asking yourself, why do we care about the remainder? Well, we care about the remainder because that leads us to our next theorem, factor theorem. Factor theorem states if we let p of x be a polynomial, if there is a remainder of 0 after dividing by x minus a, then x minus a is a factor of p of x. Conversely, if x minus a is a factor of p of x, then there will be a remainder of 0 after dividing by x minus a. Well, think about that. Trying to list factors of, say, 48. We know that 48 is 6 times 8, so if I divide 48 by 6, I get a remainder of 0. That's what makes something a factor. Factor is a number that you multiply by another number to get a third number. So factors always have a remainder of 0, and that's true for polynomials as well. So let's determine if x plus 6, x plus 5, and x minus 2 are factors of p of x equals 3x to the 6th plus 2x to the 5th minus 73x to the 4th plus 132x to the 3rd minus 36x squared. We're going to use this information to factor p of x completely. The way that we're going to determine whether these binomials are factors of p of x or not is by looking at their remainders. If they have a remainder of 0, then we know it's a factor. Since we're supposed to factor p of x completely, that's our end goal, I'm going to use synthetic division for testing remainders because I'm going to have to factor eventually anyways, and division accomplishes the factoring for me. So let's start by checking x plus 6. We're going to synthetically divide. So that's a -6 on the outside, and our coefficients underneath. Notice that our p of x does not have a linear or constant term, so I'm going to put 0 placeholders at the end. We actually need 2 of them. And now we'll synthetically divide. We drop our first number straight down, and then multiply it by -6. It's -18. Add down, -16. Multiplying that by -6, I get 96. Add down, it's 23. 23 times -6 is -138. Add down, get -6. -6 times -6 is +36. Add down, we get 0. 0 times -6 is 0. Add down, we get 0. 0 times -6 is 0. Adding down, we get 0. The last number is always our remainder. Since we have a remainder of 0, yes, x plus 6 is a factor. Well, we can already start factoring p of x. P of x factors into x plus 6 times another factor. That other factor is the quotient we got when we divided. We divided a 6th degree by a 1st degree. Therefore, the degree of this quotient is going to be 5th degree. That's 3x to the 5th minus 16x to the 4th plus 23x to the 3rd minus 6x squared. Great. Now let's move on and check x plus 5. The point of what we're doing ultimately is to factor p of x completely. So think about when you first started doing factoring. Even before polynomials, our first kind of factoring was prime factorization of a number. So if we go back to 48, right, when we did prime factorization, we would say that this was 2 times 24, and 2 was a prime number. So then we continued to try to factor 24, and we thought of what 2 numbers multiply together to give me 24, 3 and 8. So 3 is another prime factor. That's essentially what we're trying to do with p of x. Note that 3 was a factor of 24. And since 24 was a factor of 48, that makes 3 a factor of 48. Therefore, if I want to check to see if x plus 5 is a factor of my original polynomial, all I need to do is check x plus 5 in this 5th degree polynomial factor here. Because if x plus 5 is a factor of that, then it'll be a factor of the original p of x. We could check it in the original, but that doesn't help us factor the polynomial. So we want to try to break it down further. So let's divide it into the 5th degree factor. Our 0 of -5 goes on the outside and our coefficients underneath. This is going to require two placeholders at the end. We drop down our first number. That's 3 times negative 15 is, or I'm sorry, times negative 5 is negative 15. Adding down, we get negative 31. Times negative 5, that's 155. Adding down, it's 178. Multiply that by negative 5, it's negative 890. Adding down, negative 896. Multiply by negative 5, it's 4,480. Add down, we get 4,480. Multiply by negative 5, that's negative 22,400. Add down, we get negative 22,400. The last number is always our remainder. So we take a look at that remainder. It is not 0. So that tells us no, x plus 5 is not a factor. Next, we need to check x minus 2. Again, we're trying to break down that 5th degree factor, so we want to divide the x minus 2 into that 5th degree factor. Setting up our synthetic division, that's a positive 2 on the outside, and our coefficients underneath. Still needing the two placeholders at the end. Now we divide. This time we get a remainder of 0. Since we have a remainder of 0, that tells us that yes, x minus 2 is a factor, not only of that 5th degree factor, but our original polynomial. We're going to use the fact that x minus 2 is a factor of this 5th degree polynomial to factor it further. P of x can be factored then into x plus 6 times x minus 2 times another factor, and that other factor is the quotient that we got when we divided by x minus 2. We divided a 5th degree by a 1st degree, so the quotient, the degree of this quotient is going to be 4th degree. 3x to the 4th minus 10x to the 3rd plus 3x squared. We want to factor this completely. We want to get down to prime linear factors. Since we don't have any other given binomials to check, we want to factor this 4th degree factor using other techniques. Notice that that 4th degree factor has a common factor of x squared. We can factor that out. I'm going to put it at the front just because we like monomial factors at the front. That'll leave us with 3x squared minus 10x plus 3. We have a quadratic trinomial there that can be factored either by trial and error or the AC method. Either way, it factors into 3x minus 1 times x minus 3. We've factored p of x completely. P of x equals x squared times x plus 6 times x minus 2 times 3x minus 1 times x minus 3.